So this is going to be hopefully a really fast video lecture. Um, Most of what we're looking at today is review from 10th grade chemistry. Just a few little pieces of extra stuff that IB throws into this section on ionic bonding and covalent bonding. So our essential ideas, the one related to ionic bonding, ionic compounds, of course, consist of ions held together in lattice structures. We'll talk about what a lattice structure is in a couple slides. Then covalent compounds are formed by the sharing of electrons. So looking at ionic compounds first, so ions are formed when one or more electrons are transferred between atoms. So we're moving electrons. When things gain or lose electrons, they end up with a charge that turns them into ions instead of atoms. Two kinds of ions that you need to know. Cations are positively charged. They have been oxidized. This word oxidation means that electrons have been lost. So you lose electrons, you're oxidized. Anions, on the other hand, are negatively charged ions that have been reduced, which sounds really weird because how can you get electrons and be reduced? Because we know that we're negatively charged anions have gained extra electrons. So how this works, how this vocabulary, this very strange vocabulary works is this: you gain electrons, your charge gets more negative. That's the reduction part. Your charge has gone down. Let's say that I had a neutral atom, it had a charge of 0. It gained 2 electrons that had negative charges. So when I do this calculation, I get a -2. My charge went from 0 down to 2. It was reduced. So our mnemonic for this, Leo says GR, lose electrons, oxidation, gain electrons, reduction. Lose electrons, oxidation, gain electrons, reduction. Leo says GR. Good. So this is a lovely animation showing what happens in ionic bonds. So sodium just gave an electron away to fluorine. It gave that valence electron. Here it goes again. So that one valence electron sitting on sodium is transferred to fluorine. Sodium now has one less electron. It gives it a positive charge. Fluorine has an extra, it has a negative charge. Those oppositely charged ions are attracted to each other in a force called electrostatic attraction. They stick together like little magnets, electrostatic attraction. So oxidation states to know, make sure that you have annotated your periodic table or just know these in your head. So group 1 is going to have a charge of +1 because it's going to lose 1 electron. These guys are going to have a charge of +2 because they lose 2 electrons. Those 2 valence electrons get lost. These guys are weird. We don't get them oxidation states. Boron is going to lose 3, leaving a charge of +3. I'm going to switch over to the other side. So our noble gases have charges of 0 because they neither gain nor lose electrons most of the time. Fluorine is going to have a charge of -1 because it's going to gain 1 electron to get to that octet state. Oxygen is going to have a charge of -2. Nitrogen and friends here in this group are going to have charges of -3. And then carbon's the weird guy in the middle, which could be a +4 charge or a -4 charge, or somewhere in the middle. Most of the time, he's going to share his electrons. So on that opening slide, we talked about this idea of a lattice structure. So lattice structures are repeating pieces that all connect to each other. So when we talk about molecules, if I have a molecule of CO2, I've got carbon and I've got oxygen, and they're stuck together just like that. And this is one full piece of CO2. It's a molecule. In our lattice structures, ionic compounds, what happens instead is that I have chlorine stuck to sodium, stuck to another chlorine, stuck to another sodium, stuck to another chlorine, stuck to sodium, to chlorine, to sodium, to chlorine, to sodium, to chlorine, to sodium, and it just keeps going. So we have these pieces in repeating units that are all stuck to each other. So rather than have a discrete chunk of molecule, we have instead, we can see the vocabulary, we instead have the idea of we instead have the idea of formula units. So formula units in ionic compounds instead of molecules, formula units. So the formula unit is going to be this, because this is the repeating piece. It is NaCl. But salt is not just one Na and Cl. Instead, it is the repeating Nas and lots of Cls over and over and over. Because there are so many things all stuck to each other, there are some properties of ionic compounds that are pretty common. They have high melting and boiling points because it's really hard to get these magnets, this electrostatic attraction, to unbreak when we're talking about this one and this one and this one and all of them all stuck together. Solid ionic compounds are not going to conduct electricity most of the time. That's because electricity is all about the movement of charges. And if these guys are stuck in this crystalline lattice shape, they're not moving, and so we don't have electricity. However, if we can get that really, really, really crazy high melting point applied to our ionic compounds, we can melt salt, which is a crazy high temperature. Then we are going to have electrical conductivity, because if I melt this, then these guys are moving around. And because each piece has charge, and I'm getting those charges to move, we have electrical conductivity. Ionic compounds also tend to dissolve in polar solvents like water. They don't tend to dissolve in nonpolar things like oil. Because ionic compounds are so polar, they're ionic. So quick practice writing ionic formula here. If you want to pause the video and practice, here are answers. Magnesium has a +2, fluorine has a -1, and so I need MgF2, two of those to balance out that +2. Aluminum and oxygen. Aluminum has a charge of +3, oxygen has a charge of -2. We have a couple options. I can think about what are my least common multiple of 3 and 2. It would be 6. So if I have aluminum and it has a charge of +3, I need 2 of them. 2 times 3 makes 6. And oxygen has a charge of -2. I need 3 of them because 3 times -2 makes -6, and -6 and +6 balance each other out. The other little shortcut you could try, so aluminum has a charge of +3, oxygen has a charge of -2. We can just trade those numbers. And so the 2 that was on oxygen becomes a 2 on aluminum. The 3 that was on aluminum becomes 3 on oxygen. So we can just trade the charges for the subscripts. Al2O3. Good. Sodium and oxygen. Sodium has a charge of +1. Oxygen has a charge of -2. Those don't balance. I need 2 of these to balance out that -2. And so your formula is going to be Na2O. Calcium and nitrate. Be careful. This is a polyatomic ion. 8. Calcium has a charge of +2. Nitrate has a charge of -1. It's NO3 with a charge of -1. These guys are not balancing out yet. +2, -1. I need 2 of these to balance out the +2 on the calcium. However, if I just write NO3, 2, it looks like I have 32 oxygens on this formula unit. That's too many. So instead, we're going to throw in our parentheses, NO3, 2. Ammonium and phosphate. Once again, we have polyatomic ions, but this time not 1, but 2 polyatomic ions. Ammonium is NH4 with a charge of +1. Phosphate is PO4 with a charge of -3. Those don't match. We need to do some work. So we can go ahead and do our flip and switch. So I'm going to put my 3 outside my ammonium. That 1 can be an invisible 1 here. And so NH4, 3, PO4, invisible 1. Let's practice with some transition metals. Remember that our transition metals use Roman numerals to tell us what the, oh dear, my drawing, there it goes. Sorry, my pen froze for a second there. What it does, Roman numerals tell us the charges. This is a +1 on this copper. Oxygen still has a -2. Oxygen is not a transition metal. It does not need a Roman numeral. +1 on the copper, -2 on the oxygen. Cu +1, O2-, not a match. Let's do our little trick to flip and switch. Cu2O, invisible 1. Be careful, because lots of students see that Cu1 and think, oh, I need 1 copper and 1 oxygen. That's wrong. Don't do it. This guy, however, his charge is copper 2+ and oxygen 2-. These are a perfect match. And so our formula is going to be CuO because the charges cancel each other out. Be careful if you do the flip and switch. You're going to get Cu2O2. I can reduce these guys down by dividing both by 2 to get that CuO. This is wrong. This is correct. Iron 3 and oxygen, we're going to have Fe with 3+ charge. Remember that iron's symbol is Fe. Oxygen has a -2. We can flip and switch or use 6 as a least common multiple, and you're going to get Fe2O3. Lead 2 and nitrate. Lead 2 is going to have a charge of +2. Nitrate is still NO3 with a -1 charge. 2 and 1 don't match. So we need PbNO3, 2. And then last but not least, lead 4, Pb4+. That's a a big charge. Nitrite, almost the same as nitrate, but not quite. NO2 with a -1 charge. But again, we're just going to balance out our charges. I have a +4 and a -1. I need 4 of these to balance out that 4. And so our formula is PbNO2 4. Good. Let's look at covalent compounds for a little bit. Covalent compounds are formed when electrons are shared. And so this picture is very nicely showing that this electron on oxygen and this electron on hydrogen end up being shared between oxygen and hydrogen. This kind of bond is a covalent bond, and the type of compound that is made is a molecular compound. And this would be called a molecule instead of a formula unit like in our ionic compounds. Let's draw Lewis structures for atoms of oxygen and carbon. Lewis structures are going to show us how many valence electrons there are. We're just going to draw dots for valence electrons. Oxygen has 6 valence electrons, 8 total electrons, but only 6 are valence. And so I'm just going to draw some dots for oxygen's electrons. 1, 2, 3, 4, 5, and 6. And then for carbon, carbon has 6 total electrons, but only 4 are valence. And so I'm going to draw 1, 2, 3, 4. Those are the Lewis structures for oxygen and carbon. This picture is showing us the Lewis structure for carbon dioxide. In this one, they've gotten kind of fancy, and we're using X's for the electrons of oxygen and O's for the electrons of carbon. And we can see that in this shared set of electrons, 2 are carbons, 2 are oxygens and 2 are carbons, but they're still being shared. Let's talk about our rules for building these molecular Lewis dot structures. So what we're going to do is count the valence electrons for all of the atoms in the molecule. So here we have fluorine gas, F2. Each fluorine has 7 valence electrons. 7 and 7 makes 14 valence electrons. I'm going to put my F's next to each other. We always start by drawing pairs of shared electrons between the atoms. So here's one pair, 1, 2 electrons between fluorine and fluorine. Now I'm going to fill in around the fluorines so that each one has 8 electrons for a total of 14 electrons. So I've got 2. Here's 4, 6, 8, 10, 12, 14. Magic is that fluorine here has met the octet rule. He's got 2, 4, 6, 8. This fluorine also has achieved the octet 2, 4, 6, 8. These guys are shared, and so they count for both. 2, 4, 6, 8, 2, 4, 6, 8. Everybody's happy. There's our structure for fluorine. Oxygen is going to get kind of quirky. I have 6 and 6. That's only 12. So if I draw oxygen and oxygen, and I start with a pair in the middle, there's 2, 4, 6, 8, 10, 12. I have run out of electrons. There's only 12. He has 8. He only has 6. This is a problem. What we're going to do is we're going to erase these guys, and then we're going to put them in the middle instead. And so now we have 8, 2, 4, 6, 8, and 8, 2, 4, 6, 8. This is showing us that we have a double bond. So you're going to have, oxygen, double bond oxygen, 2 pairs not in bonds, 2 pairs not in bonds, 2, 4, 6, 8, 10, 12, 12 electrons on our oxygen. This is an oxygen molecule. He has a double bond. Nitrogen, each has 5 electrons. There are 2 of them. That's only 10 electrons. We went from 14 to 12 to now we only have 10. So again, if I started here, I'm going to run out of electrons. If I do this, I'm still going to run out of electrons. And so what we end up doing is making not a single, not a double, but a triple bond between the 2 nitrogens. 2, 4, 6, 8, 10. There's our 10 electrons. But if I build my Venn diagram, 2, 4, 6, 8, 2, 4, 6, 8. Triple bond between those nitrogens. Last one, hydrogen and fluorine. Hydrogen has 1 valence electron. Fluorine has 7. That's a total of 8. I'm going to put H and F next to each other. We're going to start with pairs of shared electrons. There's 2, 4, 6, 8. Fluorine is good, but oh no, hydrogen has not met the octet rule. Here's the dealie though. Hydrogen doesn't want to actually have H. 2 is good because he's only got that one energy level. The energy level number 1 has space for only 2 electrons. And so even though we have our octet rule for everything except hydrogen and helium, they have a duet rule. They're perfectly stable with only 2. Let's do a few more. So carbon dioxide. So we're going to start with figuring out who goes in the middle. Are we going to go COO or OCO? We're going to do this one. And the reason is this. The odd guy out, so I've got a pair of oxygens and a single carbon. The single guy is going to go in the middle. So we're going to put him in the middle. The other reason that carbon goes in the middle is this. Carbon has more space to make more bonds. Carbon has 4 valence electrons. That means that there's space to make 4 bonds. Oxygen has 6 valence electrons. That means that there's space to make only 2 bonds. Carbon can make more bonds. He's going to go in the middle. Carbon has 4 valence electrons. Each one of those oxygens has 6. That makes 10, 16 total electrons. I can go 2, 4, 6, 8, 10, 12, 14, 16. Oxygen looks good. Oxygen looks good. Carbon only has 4. That's not good. So what we're going to do is take some of these extra electrons. They're not extra. The electrons that are only on oxygen right now, and we're going to add them to the middle. We're going to make some double bonds. So I'm going to do carbon, double bond, oxygen, oxygen, 2, 4, 6, 8. Carbon is now pretty happy. Each of these oxygens only has 4. He only has 4, but I haven't used up all my electrons yet. I can go all the way to 16. 2, 4, 6, 8, 10, 12, 14, 16. So now carbon has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Octet rule achieved. NH3, nitrogen has 5 valence electrons. Each one of those hydrogens has 1. That's a total of 8 valence electrons. 5 from nitrogen, 1, 2, 3 from those 3 hydrogens. So since nitrogen is the odd guy out, he's going to go in the middle. He's also going to go in the middle because he has space for more bonds. Nitrogen has 5 valence electrons. That means that he has space to make 3 bonds. Hydrogen, even though he only has 1 valence electron, only can make 1 bond because he only has that first energy level. So we're going to put nitrogen in the middle. Hydrogen goes around the outside. Hydrogen never, ever will go in the middle. We're going to put our shared pairs of electrons between nitrogen and all the hydrogens. Hydrogen's happy, hydrogen's happy, hydrogen's happy. All the hydrogens are good with their 2 valence electrons. Not actually happy. They're stable, but you get what I mean. So I've used 2, 4, 6. I have 8 valence electrons. I'm going to put the last pair on top of the nitrogen. That's going to give nitrogen 2, 4, 6, 8. Octet rule achieved. Carbon tetrachloride. Carbon's going to go in the middle because it can make 4 bonds. Chloride can only make 1. He has 7 valence electrons. He can only make 1 bond. Halogens, fluorine, chlorine, bromine, iodine, they will never go in the middle. They can only make 1 bond. Carbon in the middle, chlorine all the way around. We're going to put our shared pair of electrons between carbons and chlorines. Sometimes we get excited when we think that we're done, but we need to show all of the valence electrons to build our Lewis structure. Chlorine does not yet have all of its valence electrons in the picture. So we're going to show all of the electrons on all the chlorines. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Let's make sure that's actually how many electrons we're allowed to have. Chlorine has 4. Each of those chlorines has 7. 7 times 4 is 28, plus 4 is 32. We did it. Octet rule achieved, 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 and achieved. Last one, NO3. Nitrogen has 5 valence electrons. Each of those oxygens has 6, for a total of 18. Here's the weird thing. He has a charge of -1. What does that mean? It means that he gained 1 electron. So I need to add 1 electron for the charge. Here's the 5 from nitrogen. Each of those 3 oxygens has 6, and then 1 for that charge of -1, the electron that was gained by this polyatomic ion. Add those up. 5 and 18 is 23, plus 1 is 24. We have 24 valence electrons to stick on this guy because nitrogen can make 3 bonds. He has 5 valence electrons. He can make 3 bonds. Oxygen has 6 valence electrons. He can only make 2. Nitrogen can make more bonds. He goes in the middle. Also, he's lonely. He has to go in the middle. All those oxygen friends, 3 of them, only 1 nitrogen, single guy in the middle. Shared pairs of electrons are going to go between the atoms 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 2, 4, 6, 8, 10, 12, 14, 16, 20, 22, 24. It's a problem. Oxygen's happy, nitrogen not so happy, oxygen not so happy. What are we going to do? We're going to make some double bonds. So I'm going to get rid of these guys, and I'm going to put them over here. I'm going to get rid of I feel like I counted wrong. 18, 23, 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Sorry, I counted wrong. So now we have my 24 electrons. Oxygen has 8. Oxygen has 8. Oxygen has 8. And nitrogen has 2, 4, 6, 8. This double bond could have gone anywhere. It could have gone here or here or here. We call that resonance, and we'll talk about that on Thursday. So we were looking a lot in the last couple of slides about triple bonds, single bonds, double bonds. Interestingly, these bonds come with different sizes and strengths. So single bonds can stretch out longer. Their bond length will be larger than double bonds, and double bonds will be larger than triple bonds. PM is picometers. The more shared electrons, the shorter the bond. Also, the more shared electrons, the more energy needed to break that bond. So this is showing us that a single bond between carbon and oxygen is going to have a length of 143 picometers. The double bond, only 123, and then we shrink a little bit more for that triple bond, 113. The bond energy, the amount of energy stored in that bond, it's a single bond, 358. Double bond, 745. Triple bond, 1070. More energy stored in triple bonds. Less energy stored in single. And that's true not just of carbon-oxygen, but also carbon-carbon and nitrogen-nitrogen. We can see that the more we bond, the shorter it gets, and also the more energy is stored. So this is a quick review of ionic versus covalent compounds. Ionic compounds, you have cation, anion, metals, nonmetals. Covalents are going to be all nonmetals. We're going to lose or gain electrons to get to that octet rule. They're going to share electrons to get to the octet rule. We have electrostatic attractions in both. The difference is, in ionic compounds, the attraction is between oppositely charged ions. In covalent compounds, this is kind of cool. So I've got fluorine and I've got fluorine, and I've got that shared pair of electrons in between. Fluorine's nucleus is positively charged. Fluorine's nucleus is positively charged. This cloud of electrons between them is negatively charged. There is a force of attraction between the positively charged nucleus and the negatively charged cloud of electrons between them. That electrostatic attraction, opposites attract, cloud of electrons and the nucleus. This is what holds those covalent bonds together. Ionic compounds are going to have very high melting points, more likely to be solids at room temperature, whereas covalent compounds are going to have lower melting and boiling points. They're more likely to be gases. So high volatility, more likely to vaporize. Low volatility, less likely to vaporize. Ionic compounds are more likely to be soluble in water because water is polar. Covalent compounds are less soluble unless they're polar, and we'll talk about that in another slide. Ions can carry an electrical charge if they are melted or if they're dissolved in water, whereas those covalent compounds are far less likely to conduct electricity. So we talked about those polar things. Let's focus on that for just a moment. So polar bonds are all about the differences in electronegativity. If there's a difference in electronegativity, then we have what is called a dipole moment. Di for 2, pole for like north and south or plus and minus. And so the electronegativity difference between oxygen and hydrogen. Oxygen is, hold on, let me get my data booklet. I'm looking, by the way, at table 8 in the data booklet. Oxygen's electronegativity is 3.4. Hydrogen's electronegativity is 2.2. These are not the same. And so the shared electrons here are being pulled more strongly by the oxygen. And so those electrons are sitting over here more, which results in a partial negative charge on the oxygen side of the molecule. Whereas because those electrons are farther away from the hydrogen, I've got just a little bit of positive left from that proton. This is going to be a positive, partial positive charge on the hydrogen side of the molecule. It's not like an ion where we've transferred the electrons away, but more they're just hanging out over there a lot more than they're hanging out over here by hydrogen. That results in the poles, plus pole and minus pole. I have one side negative and one side positive. This dipole moment is the result of polar bonds. So how do we know if bonds are polar or nonpolar? Well, we calculate the electronegativity difference. So carbon dioxide is CO2. I look up the electronegativity of carbon. It is 2.6. Oxygen's is 3.4. That oxygen is also 3.4. But what I'm looking at here are the bonds. So I really just care about the difference from one carbon to one oxygen, or I could look at the difference from that carbon to that oxygen. But again, I'm focusing just on this bond, 2.6 and 3.4. 3.4 minus 2.6 is 0.8. The bond is polar because 0.8 is between 0 and 1.8. H2O, same deal. I have O's and I have H's. Oxygen's electronegativity is still 3.4. Hydrogen's is 2.2. The difference is 1.2. The difference over there is also 1.2. Again, I'm focusing just on the difference in each whoopsie in each bond. 3.4 minus 2.2 is 1.2. Also polar, but these guys are not the same polar. This is more polar than this one. CH4, let's do another one. CH, 4 H's. Again, I only care about the difference per bond. Carbon is still 2.6. Hydrogen is 2.2. The difference is 0.4. Still polar, but just a tiny little bit polar. So polar covalent are not all the same. We can have very polar or we can have just barely polar. They're not all the same. Oxygen, well, oxygen is 3.4. The other oxygen is also 3.4. The difference is 0. This is going to be nonpolar or purely covalent. Good, let's practice naming and then we are done. So naming covalent compounds, the first guy does not get a prefix if there's only one. The second guy always gets a prefix. Prefixes are going to be mono, di, tri, tetra. Tetra is the one that usually tricks us up. Remember that tetra is 4 because if you've ever played Tetris, each one of those groups of blocks is formed from 4. 1, 2, 3, 4. Or sometimes it looks like that. 1, 2, 3, 4. Or sometimes it looks like this. 1, 2, 3, 4. So Tetris is a game played with these clumps of 4 little squares. Tetra is 4. Tetra is 4. Pentahexa, hepta, octa, nona, deca, those are usually matches for math. It's tetra that tricks us up. CO. There's only one carbon. I don't have to give it a prefix. It's just carbon. There's one oxygen. The second guy always gets a prefix. It's going to be mono, but if I said monoxide, that's really weird. So instead we just say monoxide. Carbon, once again, I only have one. He's going to be just carbon. I've got 2 oxygens, dioxide. 2. I've got 2 nitrogens, so I do have to add a prefix, dinitrogen. Only one oxygen, monoxide. One nitrogen does not need a prefix, nitrogen, dioxide. So I've got those 2 oxygens. I have 2 hydrogens. I'm going to call it dihydrogen. One oxygen, second guy always gets a prefix, monoxide. Yes, it's water. It is also dihydrogen monoxide. Last but not least, P2O5. 2 phosphoruses, 2 phosphori, diphosphorus. for us 5 oxygens, pentoxide. Again, we kind of skip some of the letters in the middle instead of pentaoxide, which would be really weird to say. Pentoxide is a lot easier because chemists sometimes are all about speed. Notice that the first guy, his name, the end of the name doesn't change. The second guy changes to "ide" every single time. One more slide. Let's talk about how to name acids. So there are 2 kinds of acids that we need to know about. We have these guys that are binary because they're made of 2 things, hydrogen and one other thing. 1, 2. Yeah, over here you're like, but wait, there's 3 things, 2 hydrogens and a sulfur. There's only 2 elements, hydrogen and sulfur. So even though we have multiples of the same element, we still only have 2 elements. That makes it binary, 2 elements, hydrogen and something else. Down here, I've got more than 2, hydrogen and 2 more things. That's 3, that's more than 2. No longer binary. We call these guys oxyacids because they always have oxygen, and they're made by throwing hydrogens onto polyatomic ions. Let's talk about how to name our binary acids. Always hydro something ic acid. Binary acids, always hydro something ic acid. This guy is stuck on chlorine. That makes it hydrochloric acid. This guy's stuck on fluorine. That makes it hydrofluoric acid. This guy's stuck on sulfur. That makes it hydrosulfuric acid. Binary acids, hydrogen and only one other element, hydro something ic acid. Oxyacids, no hydro. We're going to drop that hydro part of the name. Instead, we're going to figure out what is the name of the polyatomic ion. If it ends in 8, we're going to turn it into an ic acid. This is nitrate, which makes this acid nitric acid. Notice no hydro. This guy is nitrite. Nitrite turns into us acid. This is nitrous acid. This is sulfate, which means that this is sulfuric acid. This is sulfite. That means that this is sulfurous acid. If you're wondering why there's only 1 hydrogen here and 2 here, it's because of charges. The charge on nitrite is -1. The charge on hydrogen is +1. +1, -1 balance each other out quite nicely. Sulfite's charge is -2. Hydrogen is still a +1. So I need 2 of those +1s to balance out that -2. And that, my friends, is the end of our lecture on ionic and covalent compounds.